In this video, I want to show you a few examples of how to find the domain and range of a curve defined through parametric equations, and obviously followed by sketching. So the first example, we've got x is defined to be 4t plus 3 and y is defined to be 1 over 2t minus 1 for t greater than a half. So without attempting to find the Cartesian equation, what we can do to find the domain, we need to consider what happens to the possible values of x when t is greater or equal to a half. So for the domain, let's first of all substitute t equals to a half into the x definition. So that will give me 5. So this is, as you can see, this is in a linear relationship. So if I were to sketch t's against x's, so t's across x's would go on the vertical axis, it would be a straight line going through 4 with a gradient of 4. So going through 3 with a gradient of 4. So for x is greater than a half, for t is greater than a half, I will be hitting the point with the coordinates a half and 5. So we are talking about this part of the straight line. So as you can see, x's are greater or equal to 5. Also, x's are real values because it's a continuous function. You didn't need to sketch it to see that its x's are getting bigger and bigger as t's are getting bigger and bigger. For the range, we need to carefully consider the graph of y equals to 1 over 2t minus 1. This is a reciprocal graph, and remember, for the reciprocal and quadratic graph, always sketch it because they are more tricky to establish the range of those values of y. So if we plot y on the vertical and t's on the horizontal, so this is a reciprocal graph shifted down. So the asymptote is going to be y equals to minus 1, and the other asymptote is going to be t equal to 0. So when y is going to be equal to 0, when 1 over 2t minus 1 is equal to 0, so 1 over 2t is equal to 1, giving me t is equal to a half. So it will pass through a half on the t-axis, so it's going to be positive because it's a reciprocal normal, just slightly scaled and then shifted down. But on this diagram we are considering only t is greater or equal to a half. So here's a half. For t is greater or equal to a half, we are only going to be considering this part of the graph. So these are pretty much gone, they are not part of our solution, so we only have these this section of the top right branch. So if you look across, we are going to get all the y values from 0 to minus 1, not including minus 1 because you will not reach the asymptote. So this is the range. Y's are between, not between minus 1 and 0. What you could have done also is substituted the values into this function. So check what happens for t equal to a half, because that was a cutoff point. So you get y equals to, as you can see, that is going to be 0. This is going to be that point. Then check some more values. So as t gets greater than a half, so maybe try 10. What happens to y? So it's 1 over 2 times 10, so 1 over 20 -1, so that's going to be -19/20. So you could see that it goes into negative values, but it's still above -1. You can check it on the calculator. You can even use the table function. So if you put, let's say, t is equal to 10,000, what will happen there? We go that. Hold on a second. There you go. So it's going to be 1/2 times 10,000, so 20,000 minus 1. You can see it's minus 0.9999995. So it is almost -1. In fact, you'll never get to -1, although I suspect in the calculator, if you put a big enough number, the calculator will eventually round it to -1. So you need to remember that this is an asymptote. So you're better off sketching it, really. Okay, so let's have a look at this one. Very similar example. Let's see whether we can work this one out. So for this one, for the domain, I'm not going to necessarily sketch it because it's a straight line with negative gradient. All I need to do is consider what happens when t is equal to 2, and I know the line is going to go with negative gradient downwards. So starting from t equals 2, we are going to get x equals to 3 minus 4 times 2. So that's going to be -5. So -5 is going to be cutoff point, but for t is less than 2, so actually let's sketch it because it's slightly, for t greater than 2 you would be going downwards, but for t less than 2 you're going to think about that line goes through 3 with negative gradient. So this is going to be 3/4 somewhere here, and then over here we're going to have -5. So can you see that the line here is going to be all the x values, because that we're looking for possible x values of that graph. It's going to be anything greater than -5, and that's the domain. And the second function, if you consider the possible values of y, I would always sketch it. It's a simple reciprocal graph. Okay, it's multiplied by t, but if you can sketch 1/t, 2/t will look in a similar way. So we'll have two asymptotes. Vertical and horizontal axes will act as asymptote, but it's added 1, so it's shifted 1 unit. So it will go through, the asymptote will shift up to y equals 1. So you will have those two branches sketched. You can work out what that value here, so when y is going to be equal to 0, that will happen for t is equal to -2 when you solve it, so that's the value. However, we are only considering for t is less than 2. So here's 2. Let's find what we get when we put t equals 2 into the function. So it's 2/2 plus 1. That gives me the value of 2. So you're going to hit 2 over here, but not quite belonging to the graph. So for t is less than 2, we will have this part of the top branch. So we're not going to consider that one. But we also have this branch with the break for the asymptote. So the range will be all the y values all the way up to the asymptote, and then from 2 upwards. So less than 1, but also greater than 2. Okay, this should also say t cannot be equal to 0, by the way. Okay, so with this example, we are going to look at, so this is the example of how to identify the range and the domain of a function defined by parametric equations involving trigonometric functions. So this is example 3. So the possible values of x, if you consider the graph of x equals 5 cos t, so t will act on the horizontal axis and x will act on the vertical axis between 0 and 2 pi. Let's just think about what the cos graph looks like if you sketch it. 5 cos t looks like when you sketch it between 0 and 2 pi. So for 2 pi and 0, you're going to stretch it up to 5, and from pi it will go to -5. So the possible values over here, this one is not belonging that part of the graph, but because we've got this one, we'll still have that in part of our possible values of x. So the range for that particular graph is our domain for the original curve. So the domain are all possible x's between -5 and 5, including both end values. Now for the range, we need to consider the graph of this function, y equals 5 sine t. So again, let's just sketch it. Sine t between 0 and 2 pi, not including the value for 2 pi, and stretched by the factor of 5. So you could see again, these are the y values plotted against t. Possible y values will represent the range of our function. So we'll hit that spot definitely, and then we'll hit the lowest value as well, so the minimum. So the range are all values of y between -5 and 5. So with this one, we are going to have x equals cos theta and y equals cos 2 theta. So possible values of cos between 0 and 2 pi without sketching. We know that cos varies between -1 and 1, so that is the domain. So possible value of x's are between -1 and 1. Now this one, we are going to sketch cos 2 theta, so this is just a squashed cos graph. Again, we are going to, let me just sketch it, so it will appear twice within, so this will go up to pi, and then again up to 2 pi, not stretched at all, so it varies between -1 and 1. Okay, we don't have that part, but we have that, so the range is between -1 and 1. Okay, so what I haven't done, just go back to the first graph, I haven't sketched it. So the best way to sketch it is to find the Cartesian equation. So sine squared t plus cos squared t is equal to 1. That's the graph we need to consider. So if you rearrange y equals 5 sine t, you'll get sine t is equal to y over 5. If you sketch x equals to 5 cos t, so cos t is x over 5. So multiplying it out, you get x squared plus y squared is equal to 5 squared, which is 25. So that's going to be the circle centered at the origin with the radius 5. Okay, with this one here, again, let's find the Cartesian equation. So we're going to use the cos 2t, definition of cos 2t in terms of cos theta. So remember, with the double angle formula, cos 2 theta can be written as 2 cos squared theta minus 1. So over here, our x can be replaced with cos. So we are sketching 2x squared minus 1. between the values of -1 and 1. So it's going to be x squared to x squared, so a parabola shifted down to the minimum point of 0 minus 1. X squared is equal to 1 over 2 when you try to find the intercept with the, if you want to, with the x-axis. So that will give me x is equal to 1 over square root of 2 plus and minus. So these are the values. And when x is equal to -1, we should have -1 for the y values and sorry, 1 for the y values and the same for plus. Let's just check. If I put -1 here, it will be 2 times -1 squared, so it's 2 minus 1, that will give me 1. So we're going to have, there you go. And we've got both endpoints belonging to the graph. So with this example, we've got x is equal to t squared and y is equal to another quadratic, t plus 1 and t plus 2. So remember, when you're trying to find the domain, with a quadratic, always consider the graph of that quadratic. So if we are talking about any possible values of t, so I'm going to sketch this quadratic. X equals to t squared, that's just simply our quadratic with the minimum value attached at the origin. So you're only going to get anything equal to 0 or above. So the domain are x is greater or equal to 0. For the second one, so for the range, we need to consider the graph of this function. So I'm just going to draw it out and then find the minimum. So it goes with -1 and -2 as the roots, so it's a happy quadratic. There you go. So that will go through 2, but let's find the minimum value. So you can expand it and complete the square, or you could find what value of y you get for the halfway point, which is what I'm going to do. So when t is equal to -1.5, what am I going to get as y value? So it's going to be t minus 1.5. Sorry, still being it wrong. -1.5 plus 1, and then -1.5 plus 2. So -1.5 plus 1 is gives me -0.5, -1.5 plus 2 gives me 0.5. So this is going to be a half of 0.5. That's a quarter. So that value here is -0.25. So possible y values, we're going to be hitting that quarter, and then the whole graph will be above that value of y, and that's what the range is. Y is greater or equal to -0.25. I said you could have completed the square to find the minimum value of that function as well. This one, let's look at x is equal to ln t and y is equal to root t. Let's consider the graph of x. So you really should know that the ln t, as long as there is no restriction on its domain bar, the one that, so as long as the natural log is of the positive value, you always get the whole of range of y values, so the vertical, but because it's x's against t's, if I were to sketch it, this graph always goes through 1 and it goes forever. It looks like it slows down and as if it was trying to get to the an asymptote, but it doesn't. It actually does increase gradually, very slowly, but it is going forever. So the possible values of x, which is our domain, is x belong to the real values. You're going to get the whole y vertical axis, so our x-axis. With this one here, for t greater than 0, if you were to sketch this graph, you really should know what it looks like. It's, if you plot a few points when x, okay, t When t is equal to 0, y is equal to 0. So that definitely go starting here, but we're not going to include this point in the answer. Let's pick t is equal to 1, then y is going to be 1 as well. So let's go through 1, 1. Let's pick a strategic point, so it's just square numbers, so you'll get nice points to plot. That will go to 2. So when it's 4, 1, 2, 3, 4, that's going to 2. It's a parabola on its side. Okay, we've met that before in the textbook. So as you can see that those values again, you might be tempted to think, well, it's not going to be, it's going to tend to an asymptote, but it's not. It goes up and up and up forever like a parabola. So you're going to get y is greater than 0. That's going to be the range. Okay, and in this example, we need to find the possible values of x's when t is belonging to real values. So you should really be confident when sketching e to the power of t. So remember, you cover e to the power of t. What's left gives you the asymptote. So x is equal to -2, but your x's are on the vertical and t is over here. So x is equal to -2, and e to the power of t normally goes through 1. This one is just shifted down. So when t is equal to 0, x is going to be equal to 1 minus 2, because e to the power of 0 is 1, which is -1 shifted 2. So it doesn't really matter where it crosses, but just to remind ourselves where it is. So if t belongs to all possible real values, then the possible x's are anything from -2 and above. So the domain x's are greater than -2. Now if I sketch this graph, that's again the same trick. If you make that go disappear, what you are left with is the asymptote. So the asymptote is y equals to 5. Now when t is equal to 0, you'll have y is equal to e to the power of 0 plus 5, so it's going to give you 6. So I know there's 2t, it just means it's a bit more squashed than e to the power of t. So it's e to the power of 2t shifted 5 units. Okay, so for any possible values of t, you're going to get the range of our function. You're going to get anything from the asymptote upwards. So y is greater than 5.